Dr. Verma, did you ever post the second lecture?
Oh, no, I forgot. I'll do that after class today.
Okay.
Right? So today we'll go over numerical integration, and some of this you might have seen before in other classes. All right, okay, so this is basically the only way to, if you have an irregular shape and you want to compute the area or the volume or moment of inertia, there's no other way. When you do it using a computer, it does the same thing. It does numerical integration. So let's take say y is equal to x squared is our curve. And another way to write this is f of x. It's a function of x. So y is equal to f of x. And I ask you, give me the area under the curve in between these two lines, where this is x equals 1 and this is x equals 3. And so that one's easy. We know area will just be the integral. Area is going from the starting point x equals 1 to x equals 3. We have f of x dx. Have you ever thought about why it's f of x times dx? Do you know where that comes from? No?
Isn't it just base times height?
Yeah, it's essentially dx is what the width is, and fx is the vertical height. Okay, the y value. So this integration is basically summing up base times height for infinitesimally small rectangles. That's why it's that, just that. And so let's quickly evaluate this. So we have x squared dx. We get x cubed over 3, going from 1 to 3. We get 3 cubed, 27 over 3 minus 1 over 3. 26 over 3, 2 over 3. So 8.6667, right? That's the exact answer. There's no error in this because integration gives you the exact area under the curve. if you were to do this numerically, you would break it up into small rectangles. So let's do that. So numerically, we have the same curve. Starting at x equals 1, ending at x equals 3. Okay, so I want to make 2 boxes. And that's easy in this case because we get exactly 2 boxes. Now, well, first let's mark the points here. So points on the curve we know will be, this will be 1, 1, this will be 2, 4, and this will be 3, 9. That's the x value, that's the y value, that's x squared. Okay. All right, so boxes. How would you form 2 boxes here? So the width is obvious. Width in this case, we call it delta x is 1 for box number 1, and it's the same for box number 2. What's the height for box number 1? Say that once more. So do we use height equal 1 or height equal 4? Yeah, there's no set way. So if you say I'm using rectangles to do this integration, it's your choice. There's no right way. You either pick the first height or the second height. So let's pick the first one, and that's my first box. And the second box is here. So I'm basically computing the area in this black box in here. You see, I missed some part of the area I should include, but that's unavoidable. Whenever we do numerical integration, we will make some error. So let's see what area we end up with. So area is basically delta x times height is 1. That's box number 1, and box number 2 is delta x is 1 times height is what? Height is 4. Okay, so we have 5, which is terrible, right? This under predicts the actual area. This is the exact area. So exact area is this. And you see why it under predicts, because there's missing stuff. If you go about it the other way, so if you make boxes, the first box being 4 high, you include things that should not be there. So in that case, you will over predict. Where is this key? How do you improve this terrible approximation?
Make delta x small.
Right? You were saying? Okay, yeah, so both of you said the same thing. You make this delta x smaller and smaller, so we get more boxes, okay? So 2 main ways of improving accuracy. The first one is what you said. So use more discretizations. Discretizations just means the discrete boxes. Okay, we're breaking up a continuous curve into discrete boxes. So use more boxes, and they will be smaller. So this implies delta x will be smaller. And this will end up giving us a lower error. What is something else you might do? So I tell you, you have to use 2 boxes, no more, no less.
Can you also use a number?
You use what?
Average?
We can't hear you. All right, what were you saying? Well, if you overshoot it, you're just still using rectangular boxes. So
Yeah, I think what he's trying to say is that you would use an average value for y that's between, the lower between x and x plus delta x. So that would be basically y of x plus y of delta x plus delta x divided by 2, for example.
all right, so that what you're describing is basically take the midpoint, right? Instead
Right.
of either going with the first height or the second height. Why does it keep autofocusing? Okay, it should be good now. We take this part in the middle, and we will undercount a bit and we will overcount a bit. Okay, but hopefully that'll be a better approximation. Something else you might think of is, why use rectangular boxes? Why not make a straight line joining this point to that point? Okay, then we have a trapezoid. That's another possibility. Why stop at straight lines? Why not make that a parabola? Okay, so you can have a parabola connecting, well, you need to have at least 3 points for connecting with a parabola. So that's another way to improve your accuracy. You can use different ways of discretizing. So these are called discretization schemes. So use a higher order discretization. And we will go over the details of 2 or 3 of the most common ones and simple ones. Use a higher order discretization scheme. Okay, so meaning you can use a trapezoid instead of rectangles. Or you might use a quadratic fit. Between the points. Or a cubic fit, or so on. There's some limitations to how much higher you can go, and so usually quadratic fit is a good compromise. Okay, and then when we say we'll use more discretizations, let's see what happens. Whenever you're working with curves and integration, always try to visualize what's happening. So we basically say we create a lot of tiny boxes. right? So we have box 1 here, box 2 here, box 3 here, box 4 here, and so on. And we have many of these tiny delta x's now. So delta x. These are basically just depicting, every box has its own delta x. And again, you're not restricted to keeping delta x the same for all of the boxes. They can vary, but for the simplest case you can implement, you keep delta x to be uniform across all the boxes. All right, and then the area you would find, well, you would end up here. The area would basically be area of box 1 would be, area 1 would be y1 times delta x. Area 2 would be y2 times delta x. And so on. Okay, so area total you will end up with is y1 delta x plus y2 delta x plus y3 delta x dot 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 up until yn delta x. N is the number of boxes you cut this up. All right, and y1 is just f of x1 delta x plus f of x2 delta x, so on. Okay, so this becomes a sum of I goes from 1 to n fxi delta x. This makes sense, what I wrote here? If anything looks weird, let me know now, because this is very, very essential for things we will do in the class. Conceptually, if this makes sense, a lot of things will become very easy. All right, now I want you to, what is this? I want you to think about how this discrete sum can be related to this continuous integral. Do you see a relation here? Let me see if I can do some. Okay. So, do you see an equivalence between the continuous integral on top here and the discrete summation on the bottom here? It's the same, right? fx continuous, dx continuous, delta x discrete. Sum starting at box number 1 all the way up to n. Sum starting at x equals 1 all the way to 3. So they are exactly the same thing. Okay. All right. When would you, in a practical sense, let's say, if I ask you for the month of June, what is the average temperature? How do you do this? So, when we answer this question, then you'll realize there are some instances where we cannot do one way, but we can do it the other way. So let me just ask you a side question on the side. How would you compute average temperature in the month of June. So how would you do it? You have Google available to you. What would you do? Where would you start?
Just add up all the temperatures of each day and divide them by the days.
Okay, what were you saying? Same, okay. You Google each day's temperature, add it all up, divide by 30 or 31. June has 31, so divide by 31. Is that the best you can do? So think about what the temperature might look like. So if we have temperature on here and day here, on day 1, the temperature value might be something here. Okay, on day 2, it might go up. And day 3, come down, and then up, and really up. Okay, so is averaging the best way to do this? Basically, averaging it all and drawing a straight line. What else could you do?
Do it by the micro.
Do it by the what?
The microsecond.
The microset?
No, like millisecond or second.
Okay.
Like get the
Yeah, so you're basically saying have more data points, but people usually don't record very frequent data if it's temperature, okay? Because they don't really care about keeping track of what happens every minute. So instead of just summing it up, you could think of this as describing a curve, right? And one way to find the average is take the area under the curve and divide by the total duration in days. Okay, and you can start thinking about using integration. Which formula would you use to integrate this? Would you use this discrete one or the continuous one? Which one? Think about this. Do you have a nice equation describing this curve? This is real world data. If one option is you can make a fit, okay, but that's not really exact. So that's one possibility. You make a fit and then you use the continuous integral of this form. But if you make a fit, you are making an approximation, okay? Another way is directly use numerical integration. So you see, this is delta x is 1 day in each of these. Fxi, if you pick the first height, you use these. If you start from the second height, you start here, and you just form rectangles. And you do the same thing as we did for the y equal x squared case and compute the full area. So average area would, average temperature, T average, would just be integral of T of x dx divided by integral of dx, going from x1 to x start to x end. Same here, x start to x end. This is written in continuous form. If you write the same thing in discrete form, you do this, or in discrete form, T average, Okay, you tell me, what should I write? Let's just use rectangles to keep things simple. So what should I write? You can take a look at the formula given here and think about how to convert this into a discrete form. One at a time. What happens to the numerator? What happened to fx dx? It became fxi delta x. What happens to tx dx?
So you get TXI delta X.
Yeah, you can do exactly the same thing. You take on the ith day, what's the temperature multiplied by delta x, sum over all available I values. So going from day 1 to day n. What about the denominator? Say that once more. N? It would be n times delta x, because you do the same thing. You do a summation I going from 1 to n. Dx becomes a delta x in discrete form. So you sum up delta x n times. If everything, if it's uniform box sizes, this is always 1 day. So you get n days. Each interval might be different size, so this is more general. You can even put a delta xi, but that's fine. Is that good? So if you're comfortable changing a continuous integral into a discrete summation, you basically can do many, many things just using that concept.
So
All right.
the numerical is the numerical the discrete form?
Yeah, so this is analytical integration, this is numerical integration. Can you code the top one in MATLAB or Python or Excel? You can't. It's doing analytical integration. Well, MATLAB has a symbolic toolbox, so you could, but it's messy. This is a simple way. You give me values for all the TIs. So TXI, you can also call TI. So T1, T2, T3, T4. I write a for loop where I just multiply the T and the delta X and sum it up. That's it. Okay. So I'll give you assignments to do that. And here, the way I've written it, this is which height am I taking? Am I taking the first height or the second height? Yeah, correct. The first height, because I equal 1 means I'm taking this height here. If I said I plus 1, I would be taking the other height. And in this case, you're free to use either choice. And if you decide to use a different discretization, meaning if you decide to use trapezoidal rule, we would write this slightly differently. Just this first part would change. Okay, and we'll get to how we do all of that. Let's talk about midpoint rule. And visualizing each of these rules is the best way to really get an intuitive feel. So I'll draw a lot of graphs. We have y-axis here and x-axis here. And let's say we have our arbitrary curve. going from x equal a to x equal b. Okay. Midpoint says halfway in between. What is the y value? So what is f of a plus b over 2? If you know the equation of the curve, you can find out any y value you want. You just need the corresponding x location. What would you do if we go back to the temperature example? What if I told you to use midpoint rule here? So my A would be, well, let's only do one partition at a time. So A would be this guy, B would be this guy. What do you do in between? Can you find out the midpoint here? You are making an approximation when you do that, right? You don't know what the midpoint value is. So another thing you can do is you can say, this is my A, first point, this is my B, and midway is my A plus B over 2. And then you can use the midpoint rule that way, okay? So again, when you implement all of that, it'll become more clear. So midpoint rule says we form a rectangle using this box. And you can see the area is more or less what it should be. And the reason for that is in this part, the curve is relatively flat. But it's better than either choosing the f of b or f of a. You include some that you shouldn't, and you exclude some that you should have included. So they sort of cancel out. Right. So in this case, we write area is f of a plus b over 2 times b minus a. B minus a is delta x. Is everyone absolutely clear on what this means? Tell me now if it's even a little bit fuzzy. What does this mean, f of a plus b over 2?
That's the height at the midpoint.
Yeah, so we find midway through the two extremes, that's a plus b over 2, and what's the height of the curve at that point? That's basically what it represents, okay? And b minus a is our delta x here. All right. Next one, let's talk about rectangle rule. I'm drawing the same curve for all the different rules, so it's easy to look at the differences. And of course, my blue curve is f of x. All right. Again, when you tell me to integrate, you will say, I want the area between point, some starting point and some ending point. All right, rectangle rule, we either form a rectangle that's low down here, or the second option is take that guy. Right. Here we have area is f of a times b minus a. Here we have area f of b times b minus a. Okay, simple rectangle. Then we have something more sophisticated. We have the trapezoidal rule. Great, I want to make a trapezoid. What do I do? How do I enclose the box? So don't think in terms of formulas. Think in terms of visually, what do we do? Yeah, you draw a straight line going from this point to the other point. All right. So that's our trapezoid. You see, this is very, very nice. We miss some and we include some extra, but it's already looking very, very good. Okay. And well, again, just to emphasize, this height is f of b, f of b, and this height is f of a. What's the area? Right, now let's talk about formulas. So how would you write it down? Okay, so let me write that down. F of a plus f of b, the whole thing divided by 2. Yeah, times b minus a. So that's the standard formula for a trapezoid, area of a trapezoid. Height 1 plus height 2 divided by 2, that's the first part, times the width, which is b minus a. Okay. Now, when you doing this for a trapezoid is easy because we know the formula for the area. What if I fit a parabola in between? We don't have like a simple formula for that, okay? So, but what this is doing is actually it's saying, all right, I'm fitting a straight line in between. Now I have the analytical equation for this straight line, and I can do an analytical integration. Okay. When you do that, you end up with the same thing. So look at how this happens. Since we fit a straight line, between x equal a and x equal b, we can determine the analytical expression for this straight line. Okay. So I'll just draw the part of the curve that we are interested in. So here we have 0.1, 0.2. The coordinates of this guy are what? It's x, well, x equal a and y equal f of a. This guy is at x equal b and y equal f of b. One thing, when I write f of b, you understand what this means, like intuitively. For instance, if we have y equal x squared, this just means f of x is equal to x squared, which means f of x equal 3 would basically be 3 squared, which is 9. Okay, so any function you have, you just plug in the x value and you get the corresponding y value. That's all the f of b and f of a mean. Fine. Now let me connect. Yeah. Do you have a question? All right. Let's connect the two dots with the line. And what will the equation of this line look like? Y equals what? So equation of line fit. What does a general line look like? Y equals slope times mx plus c, right? So y equals m times x plus c. M and c are something we don't know right now, but we can find them out very easily because we have 2 points and 2 unknowns. M and c are unknowns. All right. So one very easy way to do this is it'll basically be okay, so we can do the whole thing. Let's see. So do you know how to solve for m and c? How? M is the slope. Yeah. You were saying, yeah, go ahead.
Plug in a point.
Yeah, we can plug in both points one by one. Plug in the first point gives us equation 1, plug in the second point gives us equation 2. Or slope is what? Y2 minus y1 divided by x2 minus x1. That's another way. So many different ways of doing this. So here, let me just write m is y2, which is, why did I write y2? Okay, I'll write it. y2 minus y1 over x2 minus x1. Which in our case is FB minus FA over b minus a. Okay, so that's straightforward. That's m. To find c, we just plug in this m here and let's see what happens. So y is equal to fb minus fa b minus a times x plus c. Okay, and we know this straight line goes through the 2 points, so we can plug in either of the 2 points and we should get the unknown c value. So let's plug in this guy. So we have fa is equal to fb minus fa over b minus a times x is what? X is a plus c. Okay. So fa times b minus a minus fb minus fa times a that guy and that guy will cancel out. Okay, so now everything is known because b and a are known to us, fa and fb are known to us. So all the unknown m and unknown c are now resolved. So our full y becomes y equals fb minus fa over b minus a times x plus c, and c is this guy. So bfa minus afb over b minus a. Okay. Once we have this, we can, well, what do we do next? Why did we find this equation? What can we do next? Say what? Yeah, we basically integrate from starting from point 1 to point B. Now we have an analytical equation. This will be a number, this will be a number, number. The only variable is x. Okay, so let's integrate and let's see what happens. So area under this line from x equal a to x equal b, okay, is basically area is x equal a to b, y of x dx. Okay, I hope I didn't make a mistake somewhere. Let's see. Okay, so this is All right, I'll do the integration directly. What happens when you integrate the first guy? This part, is it dependent on x? These are all constants, right? So it's constant times x. When we integrate constant times x, what do we get? Yeah, constant times x squared over 2. We're just integrating x dx. So we get f of b minus f of a. That remains as it was. And this guy becomes x squared over 2. Limit going from x equal a to x equal b. What about the other guy in the second term? I feel like I lost many of you. I didn't do anything here. If you just put this in here and integrate, yeah, it's just constant. When you integrate, it just becomes x. Okay. So plus, I don't have space. So plus b f of a minus a f of b over b minus a times x. Again, limit goes from x equal a to b. Is that okay with everybody? Remote students, is that okay? Integrating x gives us x squared over 2. Integrating constant gives us x. The constant parts remain the same. Okay. All right. So 2 more steps and we're done. F of b minus f of a. B minus a. This becomes b minus a. No, b squared minus a squared over 2 plus b f of a minus a f of b for b minus a, and this becomes b minus a. So that goes away. This is b minus a plus b times b plus a. So this becomes f of b minus f of a, b minus a times b plus a over 2. The same thing from there. Okay, that goes away. All right, so we have b. I feel like I'll make a mistake, but let's see. B f of b minus b f of a plus a f of b minus a f of a over 2 plus 2b a minus 2a f of b. Okay, what cancels out? Okay, one of these goes away, so a f of b and this guy goes away. What else? B f of a. So this goes away and this stays. This stays. B stays. Okay. All right. Okay, fine. B f of b. Yeah, and we're there. So we have b times fb plus fa, and the other guy is minus a times fb plus fa over 2. And see, we have what we should get. So we have FA plus FB over 2 times B minus A. Okay, so all right, yeah, I'll give you a minute to do all that. All right, so forget about all of this algebra. There's nothing. There's just subtracting, adding, nothing special happening here. The only special thing that happens is the first block here. Is this clear why we did this? Why we started here? To everybody. Okay. Let me just quickly recap. What we did was our curve here, the blue curve, if we knew the y equal fx formula for the blue curve, we didn't need to do all of this. We could have just done the full integration here. But since we don't know what the function looks like, we only know the endpoints. We say, all right, we will approximate this blue curve using a straight black line. The only thing we did was we found the equation of that straight black line, which is y equal mx plus c. That's this equation here. And once we have that, we plug in that approximation instead of our blue curve in this place. All right. And after that is just simple integration, addition, subtraction. If that concept is clear, you're fine. Instead of a straight line, what could I have? What else could I have done? Could I have made a parabola? Yeah. Although, you know, I need one more point to make a parabola because y equal ax squared plus bx plus c. There's 3 unknowns then. So I could have made a parabola, and instead of plugging in my straight line equation, I could have plugged in my parabola equation. Again, an approximation in place of my original curve. So that's it. That's what numerical integration does. And instead of doing this analytically every time, we have simple formulas for if you fit a trapezoid, you use this formula. If you fit a parabola, you use something called Simpson's rule, which I will tell you. So there's another simple formula for that, okay? But all of it comes from the same place. We do the fit, we do the analytical integration. That leads us to the relevant formula. Okay. So that's trapezoidal rule. Now, yeah, okay. So we cover what we should have. Let me tell you about Simpson's rule. Any questions? All right, so with trapezoidal rule, we have this formula, but with Simpson's rule, we use a different one. Area is equal to delta x over 6 f of starting point plus 4 times f of midpoint plus f of ending point. Okay. So if you understand what FA, FB, FA plus B over 2 are, that's it. You're done. All you need to do is write your MATLAB code. That's it. Okay. And the way to derive this is the same exact way we did for the straight line. But we're not going to do all the stuff. You can do it at home. You will recover this exact thing. The main difference you see from the top is now we need 3 different points. We need f at A, f at B, and f at midpoint. So let's write that down. So we need to use 3 points to be able to determine the parabolic fit, the quadratic fit or the parabolic fit, the quadratic parabolic fit. That we replace our unknown original curve with our original unknown curve width. Okay. So if we were drawing our sketch again with our curve here, we say we need one more point, one right in between here. And when we have 3 points, we fit a nice smooth parabola. Okay, so same as before. We take a quadratic equation with unknown coefficients, which we can find. Okay, so you would say y is the black parabola is, I don't want to use ax squared because there's an a here. How do you write parabolas? Do you write ax squared plus bx plus c? Okay, yeah, I grew up in another country, so I don't know how you do things here. There's one, what is it? Rise over run, run over rise? Oh, you write mx plus b? That's so weird. It's a constant. It should be c, not b. Yeah. Yeah, for derivatives, rise over run is what you do. Oh, okay. Yeah, I just remember delta y by delta x. All right. What was I saying? Oh yeah, quadratic. So, oh yeah, I don't want to write ax squared because there's an a here. So what should I write? I'll write lx squared plus mx plus n. Okay. Lm are unknowns. So this guy is unknown, this guy is unknown, this guy is unknown. 3 points are given, three unknowns, you form 3 equations, do the same solve. Okay. Then doing the analytical integration. Analytical integration with this parabola gives us the Simpson's rule. Formula. Right, and that's the one we wrote here. When you do all of that, you will get that formula.
What country did you grow up in?
Did you ask which country? I grew up in
Yeah.
India.
Okay. Nice.
Well, India and the Maldives. Okay, so let's actually do a simple example so this becomes a bit more concrete. And then I'll tell you about order of accuracy. Okay, so example. All right. So the question is integrate y equal sine of x. Is that enough? If we just integrate this, what do we get? Minus cosine x plus c. There's an unknown constant in there. The reason is I didn't tell you start at x equal this and end at x equal something, okay? If I don't tell you that, you need to have that c in there, but we don't want that, okay? So I'll tell you starting from x equals 0 to x equals pi over 2. All right. And again, get into the habit of making a sketch, okay? So, because this really helps understand what's happening better. So we have x equal here, y here. What should I draw? Draw what? That's cosine. Yeah, all right. We start here and then, yeah, we draw a nice clean sinusoid, all right? So we do this. Okay, it's a little big, but that's fine. So this is x equals 0. And this is x equal pi over 2. Okay. If I tell you to integrate the full period, do you know what area you'll get? Yeah, you'll get 0 area if I tell you to go from the start here to the end here. Because? Yeah, same area on above the axis, same area below the axis. So this is positive area, that's negative area. Okay. It doesn't make sense, and you shouldn't. Well, when you talk about, well, it does actually make sense. So if you say this is a weird hull, no, it doesn't make sense. Okay, mathematically it does, but if you talk about this being a physical hull, right, some weird alien shape, and you say, okay, let me draw a hull, same thing. You don't need to draw this. So let's talk about this. So we have this aliens from Halo, they have these ships, right? So, and it's symmetric about this axis. Okay, so let's see, I draw something like this. How would you compute the area of this weird hull? Do you say we have equal area above and below this axis, so area is 0? You would basically specify this to be your x-axis and this to be your y-axis. Okay, and if the aliens give you the equation for the curve, the hull shape, you're fine. You just do integration, but only for the top part. And then you can take 2 times that, okay? Another way is, you know, this is what? This is f of x. What is this? Yeah, this is minus f of x, okay? So you can basically do this integral. So you can go from x equal 0 to x equal length. So this is 0 and this is length. And you can say, all right, if I only want the top area, I integrate fx dx. But I want to go all the way from the top to the bottom, then you do a minus negative fx dx. Okay? Minus minus gives you 2 times fx. So basically doing top half and multiplying by 2. So that, even though negative area might not make sense, mathematically everything is consistent. This will end up giving you a negative area. That's why. Why did I put minus here? We're basically talking about the total height, right? So is the top minus the bottom gives you the total height. That's exactly what is written. Okay? We will use this when we compute areas of halls. Okay. Right. All right. Okay. So let's do this analytically first. So analytically, area is, what do I write? Tell me. Okay, sine x times dx and say that once more. Yeah, that's it. Okay, very simple integral to evaluate. So we get what? We get minus cosine of x going from 0 to pi over 2. Cosine of pi over 2 is 0, so we get minus of 0. Let's put the minus outside. So 0, negative 1. Okay, so we get 1. Right? So going from 0 to pi over 2, the area, the shaded area, this area is 1 unit squared, 1 meter squared, 1 feet squared, whatever unit you're using. Fine. Now let's use the rectangle rule. Okay, what now? Okay, let's draw a sketch. Anytime something doesn't click right away, always draw a sketch. So okay, whatever on that side, don't care. Okay, tell me, what should I do? Make a what? Make a rectangle starting here. All right, let's do that. So, okay, fine. When you make that rectangle, what's the area? Yeah, because this base is pi over 2. What's the height? Sine of pi over 2 is 1. So this is 1. This is pi over 2 comma 1. That's the coordinates. Okay, so we have area is pi over 2 times 1. 3.1415 blah 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 divided by 2, which is what? Let's see, is 1 point 2115555 and then 114.7 dot dot dot. Okay. As expected, we overestimate. It should have been 1. That's the exact value, but we get 1.57. So we make a 57% error. Is this the only option for using the rectangle rule? Pi over 2 times 1? What's the other option? Is what?
Use 0.
Yeah, you use 0.
Yeah.
So height is 0, base is pi over 2, area is 0. Okay. So, or area is equal to pi over 2 times 0 when we use the first height, which is 0. So how much percent? 100%, I guess. Yeah, so this is 100% error. Okay. Next, let's use midpoint rule, and then we'll run out of time. So midpoint rule. Again, let's draw a sketch. All right, so, okay, fine. All right, tell me, what should I do? We form a box. Base is the same, so the width stays the same. What about the height? Where? Yeah, so in between, so pi over 4. So wherever our pi over 4 lies, so this is pi over 4 comma sine of pi over 4. That's our height. So this is our box. All right, area is base is pi over 2. Height is what is the height? What goes here?
F of pi over 2 minus 0.
That's the base, right? Pi over 2 minus 0 gives us the base. What's the height?
Sine pi over 4.
Yeah, it's y value, which is sine pi over 4 minus 0. Sine pi over 4 minus 0. Okay, can somebody compute that and tell me? No, number, decimal. All right. be pi over 2 root 2. Pi over 2 root 2. What's the number?
So this said, but
No.
oh, it's in degrees. That's why.
No.
I'm on like shitty calculator.
Okay. All right. So pi over 2 times square root of 2. Okay. Remote students, come on.
It's like 1.11.
Okay. 1.11 something. Okay. So is 11% error. Okay. Look at this. We just use one stupid big box and we get within 11%, which is, yeah, you know, not terrible, but it's not good for doing actual calculations. So what do? You make many boxes and you get much better. Okay? That's what we will do. Okay, I'm out of time, so let's keep going. We'll do Simpson's rule next class and other examples. Any questions? This is very important. Make this your own. Keep it with you forever because you can use it many different places. All right, so see you guys next class.